Hi, my name is Konstantin Magnus. In this Houdini tutorial, we are going to interpolate a subdivided box through a set of closed curves to shape a subdivision model. So you can see this is not your standard sweep, but also the cap regions are subdivided and have quadrilateral polygons. The way this works is I use the KinFX rig wrangle to just shape a curve, apply a bunch of circles using the sweep node, and then apply polar coordinates to the box and use the spline function to interpolate through these circles. As per usual, you can download the example file and see the code on my Procision website. The link is in the description. There's also a Patreon button if you want to support my work. And we will now start from scratch in a new file. And in case I didn't show it, you can use any type of curves. You can also use a square, and then it would look or adapt to that shape. And you can also draw your own curves. You can use a mixed set of curves. It would all work as long as they are closed and they start and end in the same position. This is why I applied these colors. So you can see they should always start up here and go around like this. All right, in a new scene file, we would just come up with a box. And I use uneven numbers, something like 11, 11 by 11. And the idea is to apply a UV texture, more specifically polar coordinates along the z-axis, and I put this on the point class, and you can press spacebar 5 to see it unwrapped. There are room for optimizations. You could spherify the box beforehand to make this smoother, but just to get the concept across, let us now set up a bunch of curves. I'll just use a tube for now and give it a bunch of rows, so you can define how many you need. I'll come up with 5, and you should give them maybe plenty of subdivisions for a smoother result. What we need next is a way to interpolate through this. So we want the box to be connected with the circles we've just created. And now we would want to know a few things about the second input, like the number of curves. There's a function called n-primitives that counts the number of curves or primitives on, in our case, the second input. And what we want to fill is an array with positions. So vector pos and these rectangular brackets will be filled later on with a bunch of point positions. Using a for loop for integer I, 0, I smaller the number of curves, I plus plus. And now we want to find out about the position. So let's use the primuv function, which can sample the positions from these curves. Let's see this. The primuv may start here from 0, goes to 0 to 5, to 0.5, 0.75, up to 1. So we're all around one time. And you can see it here. We're now iterating through the curve numbers using I. So starting at 0, 1, 2, 3, 4, 5. Just like you can see here, that would be 0, 1, 2, 3, 4. And what we need to feed in to actually sample from it is the UVs. So as you can see here, we have two UV components, UV0 and UV1. And in my example, I have used the entire UVs, but it is only going to use the first component. So let's just try it and append it to the array. So append to the position array our P, and then we would in the end use all these positions we have collected and blend along them using the spline function. There are various different interpolation methods. We use B-spline as a base, using just one component of the UVs and interpolate through these positions. Now that's a start. You can see if you activate these circles, that is somewhat doing the job. But on the first primitive, it is still not really smoothly interpolating. It's also stretching one point across, so we definitely need to improve this a bit. And the way I've done it in my code is I used the primitive position, which is the center of the curve, as the first entry in our array, and the last entry of the array also got the last curve's position. So let's just do this. We don't need a vector then. Let's just copy this. Remove the word vector here and just paste it there. And again, we want the first curve, and after the loop, we want the last curve, which is num -1 to compensate for the fact that it's starting to count with 0, and now P should not repeat. And the idea behind this was obviously to get a smoother result, which did not quite work because at the moment it's still using the UV location around the circle, but we just want the center position like so. Now that's a lot smoother. The last point, which is up here or down there, is still a problem, so we should fit our UVs in a bit. Let me just demonstrate what we're doing here. Fit underscore UV, and I would like to use change the Y component of the UV using the fit01 function. We can then just put it between, let's say, 0.05 and 0.95, and then look at the results. So that's a lot more forgiving, and you feel free to play with this a bit to optimize this. This would tighten it up, and this would loosen it up a bit, depending on what topology you would like to get. All right, that would be the same on the other side, of course, like so. And now you can apply basically any kind of curves, so it wouldn't really care. If I make them rougher, you get this faceted look. And if you want to do the gooseneck, then you would of course replace this set with a more complex chain of commands. So let's just give it 50 points a line, and the rig doctor would give us some transforms if we initialize them, and they can be used for a roll. So we can now roll the neck a bit, or rather curl it. And this works by, first of all, providing the U, which is the relative start and end position from 0 to 1.0. Vertex curve param along the vertices gives us just that. And now we can rotate the local transforms. By some kind of amount. And the axis in our case will be the x-axis 1.0, 1,0,0, and the amount can be controlled with the ramp. So let's create a channel ramp called curl along U, and to make it curl in both directions we subtract 0.5, and for correctness we will multiply it by 2.0 later on. And now this should give us this nice curve, and as soon as we set the initial value to 0.5 it should start straight like this, and then we can basically draw the entire shape. So you would be able to say when I go below 0.5 it curls back, and when I go above 0.5 it curls to the front. Now these are regular, but I don't quite need the details, so I wouldn't recommend to change the curve's density. I rather resample it after deformation, and you can define the number of segments here by yourself. Now, one more step would be the sweep node, which shouldn't be irritated by what we feed in. So let's just delete all the transformation attributes. So let's just put an asterisk in there, and that way it has, or it comes up with its own fresh transforms, and we would switch the surface type to rows only, which are essentially circles for now. And we can give it a bit more resolution. Here under columns I use maybe 32. Now in order to get a different shape we can apply a scale, and I use just the hill with lifting up the first and last point from 0, so it has a bit of scale there. And feel free to come up with your own exotic shape. Now let's try to connect this and see the results. So at the moment it seems to work. There's just it's just like the B-spline function is not going through the points. It's doing a fairly smooth job. So what we can do now is we can change the underlying resolution of the box, and we can also change the scale of the sweep node to compensate for the really smooth interpolation, and now play with the curl in the rig wrangle. Yeah, I hope you enjoyed the tutorial, and I think it's obvious that we can also use this technique for more complex scenarios. This is just a starter for getting something like a gooseneck.